Welcome to the Deep Dive. Today we're diving into something pretty mind-bending. Quantum annealing.
It's definitely cutting-edge stuff.
Yeah, this isn't your standard laptop crunching ones and zeros. We're talking quantum mechanics, specifically tailored for tackling these monster optimization problems.
Exactly. Problems where finding the best answer is incredibly tough for regular computers because there are just so many possibilities. Quantum annealing, well, it offers a different way in.
So our mission today really is to unpack this. We're drawing heavily on a fantastic essay by Jorgo Schneppat, Quantum Annealing, QA, Revolutionäre Optimierungsmethod.
Yes, Schneppat's work gives a really solid overview, from the basic ideas to the tech and the applications. It's a great guide for our chat.
And why should you care about this? Well, think about getting a package delivered super efficiently, or designing a new wonder material, or figuring out the best investment strategy. These are all optimization problems.
They're everywhere. And quantum annealing, or QA, it holds this promise of being a game changer for solving them, potentially.
Okay, let's jump in then. Where did this whole concept even start? It didn't just appear out of thin air.
No, not at all. It actually has roots in classical computing, specifically a technique from the 80s called simulated annealing, or SA.
Simulated annealing, like heating up metal and letting it cool down slowly.
Exactly like that. The idea is you simulate that physical process. When metal cools slowly, its atoms settle into a very ordered, low-energy state.
The most stable arrangement.
Right. So the algorithm explores different possible solutions, different arrangements, and tries to find the one with the lowest energy, which represents the best or optimal solution to your problem.
So it jiggles around a lot when it's hot to explore, and then settles down as it cools.
Precisely. And there's a clever bit of math involved, the Boltzmann distribution. It allows the algorithm, even as it's cooling, to sometimes accept a worse solution temporarily.
Why would it do that?
To avoid getting stuck. Sometimes you need to go slightly uphill to find a much deeper valley later on. The probability of making that uphill jump depends on how much worse the solution is and the current temperature. PE equals XE E KB T.
Okay. Key is the energy difference. T is temperature. KB is just a constant. So the hotter it is, the more likely it is to jump.
Yep. And that ability to escape local dips is crucial. QA borrows from this basic idea, but adds a quantum element.
Okay, so how does QA level this up with quantum mechanics?
This is where it gets really cool. Instead of just thermal jumps over energy barriers, QA uses quantum tunneling.
Tunneling, like going through the barrier instead of over it.
Exactly. It's a purely quantum effect. The system can find shortcuts through the energy landscape that are just impossible classically. It opens up access to potentially better solutions hidden behind those barriers.
That sounds almost like cheating. Who figured out how to apply this quantum trick to optimization?
The foundational theory was really laid down by Katawaki and Nishimori back in 1998. They connected it to something called the adiabatic theorem of quantum mechanics.
Adiabatic.
Yeah.
Meaning you change things very, very slowly.
That's the essence of it. If you start a quantum system in its lowest energy state, its ground state, and you change the system's parameters really gradually, the theorem says it should stay in the ground state the whole time.
So you start with an easy problem you know the answer to, and slowly morph it into the hard problem you want to solve.
You've got it. And they describe this mathematically using a Hamiltonian. Think of the Hamiltonian as the recipe that defines the energy landscape. Their formula looked like HDT plus STHP.
Okay, break that down. HET is the Hamiltonian changing over time?
Right. HET is the simple starting Hamiltonian easy ground state. HP is the Hamiltonian that encodes our actual complex optimization problem. And a LINT is like a dimmer switch, smoothly going from 0 to 1, changing the system from HB to HP.
Clever. So the theory was there in 98. When did people start trying to actually build these things?
That brings us to D-Wave systems. They were founded in 1999, really pioneers in commercializing QA. By 2011, they had their first commercial system out.
Wow, that's quite quick, relatively speaking.
It is, and they've kept iterating. Systems like the D-Wave 2000Q and then the Advantage processor came later, significantly boosting the number of quantum qubits and how they could connect to each other.
And I guess the rest of the world started taking notice around that.
Definitely. Through the 2010s, you saw growing interest from both scientists and industry. People started seriously exploring applications, logistics, finance, materials science.
While also trying to figure out, how powerful is this really? What are its limits?
Exactly. A lot of theoretical work happened alongside the hardware development, trying to pin down where QA truly offers an advantage over classical methods.
Okay, so from mimicking cooling metal to quantum tunneling through energy hills. Quite the journey. Let's get into the nuts and bolts, the hardware itself. What does a quantum annealer look like inside?
Fundamentally, it's a grid or lattice of qubits. But they aren't just sitting there, they're connected by things called couplers.
Couplers. They let the qubits interact.
Precisely. These couplers allow qubits to influence each other's quantum states. That's how you actually encode the relationships and constraints of your optimization problem onto the chip. The pattern of these connections and their strengths represents that problem, Hamiltonian HP, we talked about.
And D-Wave developed specific layouts for these qubits, right? Chimera and Pegasus.
Yes, those are two of their well-known chip architectures. They describe how the qubits are arranged and connected. It's not usually an all-to-all connection. Each qubit connects directly only to a limited number of neighbors.
Why limit the connections? Doesn't that make it harder to map problems?
It does create challenges, yes. But it makes the chip much easier to actually fabricate and control reliably. If you need two distant qubits to interact strongly in your problem, you might have to use a chain of intermediary qubits and couplers to link them.
Ah, so that eats into your available qubits just to simulate a connection, a trade-off.
It's a practical engineering trade-off, exactly.
Is D-Wave's superconducting approach the only game in town for QA hardware?
It's the most developed for QA specifically, but no, not the only one. People are exploring other platforms. Trapped ions, for instance.
Using charged atoms held in place?
Right. They can have very long coherence times, which is a big plus. Photonics using light particles is another avenue. Some hope photonic systems might eventually operate at room temperature, which would be huge.
Room temperature quantum computing. That sounds much more convenient.
It would certainly simplify things. But for QA right now, these alternative like ion traps and photonics are generally less mature than the superconducting circuits D-Wave uses. They have their own challenges, often with scalability or control.
Okay, sticking with the superconducting ones for now. You mentioned needing extreme conditions. Just how cold are we talking?
We're talking incredibly cold. Colder than outer space, typically below 10 millikelvin.
Really, Kelvin? That's barely above absolute zero. How do you even achieve that?
With very specialized refrigerators called dilution cryostats. They use mixtures of helium isotopes, helium-3 and helium-4 to reach these ultra-low temperatures.
And this extreme cold is all about stopping the qubits from getting messed up.
Essentially, yes. It's about minimizing thermal noise. Heat is just atomic vibration, and that vibration can easily knock a qubit out of its delicate quantum state. This loss of quantumness is called decoherence.
So less heat means less shaking, means the quantum state lasts longer.
Exactly. You want to maximize the qubit's coherence time. QA systems are actually somewhat more robust against noise compared to universal quantum computers. But noise, decoherence, stray fields, they all still degrade performance. It makes precise calibration absolutely critical.
Like tuning a very, very sensitive instrument in a perfectly silent, frozen room.
That's a pretty good analogy, actually.
And you're always trying to pack more qubits in and connect them better, but that must make keeping everything stable even harder.
It's a constant battle. Scalability, more qubits, denser connections is vital for bigger problems. But as you scale up, maintaining stability and coherence across the whole chip becomes exponentially more challenging. It's a huge engineering hurdle.
Let's zoom in on the qubits themselves. The basic building blocks, they're like classical bits, but weirder.
Much weirder. A classical bit is 0 OR1. A qubit can be 0 AND1 at the same time, thanks to superposition.
The spinning coin analogy.
Right. Until you measure it, it's in this combined state. And then there's entanglement, where qubits can be linked. Measuring one instantly influences the other, no matter the distance. These quantum properties are the resources QA uses.
You mentioned different physical types. Superconducting ones are the most common for QA.
Yes, used by D-Wave and others. They're based on superconducting circuits with components called Josephson junctions. They work at those ultra-low temperatures. Pros are relatively fast operation and mature fabrication. Cons are sensitivity to noise and decoherence.
And the ion traps. You said longer coherence times.
They do. You trap individual ions with electromagnetic fields and use lasers or microwaves to control their quantum states, usually internal energy levels. Great coherence, but scaling up to thousands of precisely controlled ions is really, really hard.
And photons, using light.
Yeah, using properties like the polarization of single photons. Big potential advantages like room temperature operation and integration with fiber optics may be good for quantum communication too. But for large-scale QA, they're less developed currently than the superconducting qubits.
So across all these types, the big challenges are keeping them stable and coherent.
Absolutely. Stability means resisting noise, temperature fluctuations, stray fields. That needs shielding, careful design, error mitigation. Coherence is about how long that fragile quantum state lasts before decoherence ruins it. For superconducting qubits, we're talking microseconds.
Microseconds doesn't sound very long.
It's long enough for the annealing process in current devices, but making it longer is a major goal. It would allow for slower, more careful annealing, potentially leading to better solutions for harder problems.
Okay, so a huge amount of effort goes into just creating and maintaining these delicate quantum states. Now, where's this actually being used? Let's talk applications.
Optimization is the name of the game. Finding the best way to do something when there are countless options. Industry is full of these problems.
Like what specifically?
Logistics is a classic example. Think package delivery routes, the famous traveling salesperson problem, or the more complex vehicle routing problem, VRP. How do you minimize distance, fuel, time, given vehicle capacities, delivery windows, traffic?
Stuff that delivery companies grapple with every single day.
Exactly. Or optimizing warehouse layouts, managing complex global supply chains. These problems can have so many variables and constraints that classical computers really struggle, especially if you need answers fast.
How does QA help with, say, the VRP?
You formulate the problem mathematically, often asking, does vehicle X travel directly between location I and location J? Yes or no, a binary choice. The goal is to minimize the total cost, like distance, based on these choices. QA's ability to explore many combinations simultaneously might find better routes faster, especially for large, complex networks.
Makes sense. What about finance? That seems ripe for optimization.
Absolutely. Portfolio optimization is a big one. How do you choose a mix of stocks, bonds, other assets to maximize expected return while minimizing risk?
The eternal balancing act.
Right. Finance also involves optimizing trading strategies, managing risk exposure across many correlated assets. Again, these can become incredibly complex calculations. QA offers a different way to search that vast possibility space.
And you can express that portfolio problem mathematically, too.
Yes, a common way is maximizing expected return minus some factor, lambda, representing risk aversion, times the variance of return. Maximize ERRR. Finding the optimal weights for each asset in the portfolio is the challenge QA might tackle. And big players like Goldman Sachs, JP Morgan Chase, they are definitely looking into this.
Okay, beyond logistics and finance, what about AI and machine learning? That seems like a hot area.
It is. One potential application is speeding up the training of neural networks. Training these deep learning models involves finding the best settings for millions, sometimes billions, of internal parameters, weights, and biases.
That's a massive optimization problem right there.
It really is. You're trying to minimize an error or loss function. QA could potentially navigate this complex error landscape more efficiently than traditional methods, finding the minimum, the best parameter settings faster.
So faster training times for potentially better AI models.
That's the hope. The loss function might be LWB, 1n times the sum of errors for each data point, where W and B are the weights and biases you're tuning. QA could help find the W way that minimize L.
What about hyperparameters, things like learning rate or how many layers the network has? Choosing those seems like optimization too.
Absolutely. Finding the best hyperparameters is often a frustrating, time-consuming trial and error process. It's a combinatorial search problem. QA's ability to explore many combinations could make finding the optimal hyperparameter settings much more efficient.
Interesting. Let's switch gears to the physical world. Material science, chemistry.
Huge potential there. Designing new materials often involves finding the optimal arrangement of atoms or molecules to achieve specific properties, strength, conductivity, magnetism, whatever you need.
Like molecular level Lego.
Kind of. You can represent the energy of different atomic configurations using a Hamiltonian, maybe something like some G sigma, some high sigma, where sigmas represent atomic states, and J and H describe interactions in fields. QA could find the lowest energy configuration, predicting stable structures with desired properties.
And simulating how molecules behave. Drug discovery.
Yes, simulating chemical reactions, predicting molecular interactions, finding the lowest energy shapes of complex molecules like proteins that's crucial for designing new drugs or catalysts. QA offers a quantum approach to these fundamentally quantum problems.
It seems like the applications are really diverse. Any other surprising ones?
Well, people are looking at genomics, analyzing gene sequences, understanding protein folding, which is again an energy minimization problem, and smart cities optimizing traffic light timings in real time, managing traffic flow, planning routes for autonomous vehicles, basically anywhere you have a complex system needing optimization.
Okay, the potential seems enormous, covering so many areas.
Yeah.
But let's be realistic. What are the roadblocks, the big challenges holding QA back right now?
There are definitely significant challenges. On the technical side, decoherence and noise remain major villains. As we said, the quantum states are incredibly fragile.
They lose their quantumness easily.
Right. Environmental interactions, thermal noise, electrical noise. They all conspire to kick the system out of its delicate state, potentially disrupting the annealing process before it finds the true minimum energy solution. That's why the cryogenics are essential, but they add immense cost and complexity.
And even with the cold, it's not perfect.
Not perfect. Noise can still cause errors or prevent the system from perfectly following that slow adiabatic path. Mathematically, you can model this noise using terms added to the ideal quantum evolution equation, like dat IH plus L, where L represents the messy effects of the environment.
Beyond the fragility, what about the scale? Are the machines big enough yet?
That's another key limitation. Current annealers have thousands of qubits. That sounds like a lot. But many real-world problems, when mapped, might require tens or hundreds of thousands or even more.
And the connectivity issue we discussed.
Yes, the limited connectivity in architectures like Chimera and Pegasus is a constraint. Because not every qubit can talk directly to every other qubit, you often need to chain qubits together to represent a single logical variable that needs many connections. This embedding process uses up physical qubits, reducing the size of the problem you can actually fit onto the chip.
So technical hurdles in building and controlling the qubits. What about theoretical limits? Is QA guaranteed to beat classical computers?
No, and that's really important. QA is not proven to solve NP-hard problems efficiently in general. It's a heuristic method, like simulated annealing. It might find very good solutions quickly for some problems, but it can still get trapped in local minima.
Those annoying small dips again.
Exactly, especially for very complex problems with rugged energy landscapes. The ideal adiabatic theorem assumes infinitely slow evolution, but real annealing happens in finite time, making it imperfect. So no guarantees of finding the absolute global best solution every time.
And does the difficulty scale well? If I double the size of my problem, do I just need double the qubits?
Unfortunately, it's often much worse. For many problems, the number of qubits required might grow exponentially with the problem size. So even with improvements, we could quickly hit hardware limits for really large instances. Plus, there's the overhead of formulating the problem itself.
Formulating, you mean translating the real-world problem into the language the annealer understands?
Yes. Often you need to convert your problem into a specific format called QUBO, quadratic unconstrained binary optimization. Basically, minimize XTQX, where X is a vector of binary 0 or 1 variables, and Q is a matrix describing the interactions. This mapping process itself can be complex and sometimes diminishes the potential quantum advantage.
Okay, so technical limits, theoretical limits.
Yeah.
What about just practical economic factors?
They're significant. Building and running these machines is incredibly expensive. The cryogenics, the specialized chip fabrication, the control electronics, the need for highly skilled physicists and engineers. It all adds up.
So it's mostly big companies, big research labs, governments right now.
Largely, yes. Access is still quite limited. The long-term economic viability really depends on bringing those costs down and demonstrating clear, practical advantages over classical methods for commercially relevant problems.
And you need the right people too, not just the machine.
Absolutely. You need interdisciplinary teams, people who understand the quantum physics, the computer science, the specific application domain like finance or logistics, and the optimization theory. Finding and training people with that breadth of expertise is a bottleneck.
It could hinder wider adoption if we don't build that talent pipeline.
It definitely could. Investment in education and training specific to quantum computing, including QA, is going to be crucial.
So despite the hurdles, people are clearly pushing forward. What does the future look like? Where is QA headed?
Well, in research, it opens doors to tackling scientific questions that were just too computationally expensive before. Think complex simulations in climate science, drug discovery, astrophysics, problems with vast parameter spaces to explore.
Minimizing some complex function, like EP sees some Weech, phi, pj, where p are parameters in a climate model.
Exactly, things like that. QA could offer a new tool for those kinds of massive optimization tasks within scientific modeling.
What about linking QA with other quantum computers, the universal ones?
That's a really exciting prospect. The idea is synergy. Universal quantum computers aim to run a wide variety of algorithms, but they also face huge challenges with error correction and scaling. QA is specialized for optimization.
So maybe use QA as a specialized coprocessor.
Precisely. Use the annealer for the optimization parts of a larger quantum computation run on a universal machine. This could make the whole process more efficient and powerful, a hybrid quantum approach.
Speaking of hybrids, what about combining QA with classical computers?
That's probably the most practical near-term direction. Hybrid algorithms that use classical methods for some parts of the problem and QA for others, playing to the strengths of each.
Like using QA to get a good starting guess, and then a classical algorithm refines it.
Exactly. Or use classical methods to break a huge problem into smaller chunks that QA can handle. We're already seeing this approach explored in logistics, finance, even things like medical image analysis. Leverage the best of both worlds.
For this to really take off, it needs to be easier to use, right? Plug into existing systems.
Definitely. Seamless integration is key. We need better software tools, APIs, interfaces so that companies and researchers can plug QA capabilities into their existing IT infrastructure without needing a PhD in quantum physics.
And cloud platforms help here, like D-Wave's Leap.
Hugely. Cloud access removes the massive barrier of needing to buy and operate your own multi-million-dollar quantum annealing system with its dilution fridge. It democratizes access.
So potentially smaller companies, universities, startups could start experimenting and innovating with QA through the cloud.
That's the vision. Broader access fuels innovation. It could really accelerate the discovery of new applications and potentially give regions or companies that embrace it a competitive edge.
And what about the wider societal impact? Jobs?
Correct.
Education?
It's likely to have a profound effect eventually. We'll see increased demand for quantum software engineers, algorithm experts, hardware specialists, people who can bridge the gap between quantum capabilities and real-world problems.
Meaning education systems need to adapt.
Yes. We'll need new curricula, new degree programs, retraining initiatives to build that future workforce skilled in quantum technologies and interdisciplinary thinking.
It really feels like we're on the cusp of something potentially transformative, even with all the challenges.
It does. The pace of development is rapid, and the potential impact is vast across so many sectors.
Okay, so let's try to wrap this up. We've journeyed from the classical roots in simulated annealing to the quantum magic of tunneling in quantum annealing. We've looked at the complex hardware, the superconducting qubits needing near absolute zero temperatures,
The D-Wave systems like Chimera and Pegasus, and the ongoing challenges of noise, decoherence, and especially scaling up the number of qubits in their connectivity.
right? And the applications are incredibly broad, optimizing logistics, finance, training AI, designing materials, simulating molecules. The list goes on.
But we also need to remember the limitations. QA isn't a magic bullet for all hard problems. It can get stuck in local minima, and mapping problems can be tricky. Plus, the cost and expertise required are still significant hurdles.
Yet, the future looks bright, with hybrid approaches combining classical and quantum, cloud access making it more available, and the potential synergy with universal quantum computers.
And Jorgo Schneppat's essay did a great job laying out this landscape for us, the promise, the progress, and the problems still to be solved. It's clear QA has practical value now for specific optimization tasks, but it's very much a technology still growing and evolving.
Absolutely. It holds immense potential to drive future innovation, but continued investment, research, and collaboration are definitely needed. So thanks again to Jorgo Schneppat for the insights from his work.
Indeed, a very helpful guide through this complex topic.
And for you, our listeners, here's a final thought to chew on. Given those current limitations in qubit connectivity, the fact that not every qubit can easily talk to every other qubit, what unexpected fields, maybe ones where the problems naturally have sparser connections between variables, might actually see the earliest breakthroughs from quantum annealing. Something to ponder. Thanks for joining us on this deep dive.